Okay, so very excited to be here today to share with you what I've been working on. So before I really jump into things, I thought I would give a sense of sort of what the style of work that really gets me excited, which is really about the potential to leverage emerging technology to improve people's lives while working on interesting technical problems. So this coincides pretty well with the communities and topics that I consider. So they being autonomy, specifically for roadways, intelligent transportation systems, and learning for decisions and control. So I'm going to now remind you of something that we use every day, and thus it's easy to take for granted sometimes, something that we actually rely on for just, a lot of our lives. So roadways are, you can think of them as the circulatory system of the economy. They bring producers to markets, workers to jobs, students to schools, sick to hospitals, and so on and so forth. So they're critical. They're a critical piece. They are, at the same time, they're far from perfect. And so there's a lot that we can do to improve these in all sorts of dimensions. So the approach that we've been taking for the last 20 years as to how to improve roadways is what we might consider something like autonomy-driven design. So this is the idea that if you can achieve autonomy, if we can achieve autonomy, then vast societal benefits are going to be unlocked. So the reasoning goes something like this. Let's figure out perception, planning, common sense reasoning, social orientation, altruism, and maybe a few other things. And then we can use this to make roadways more sustainable. And by more sustainable, I'm going to restrict the definition here to mean that roadways are safer, cheaper, cleaner, okay? And it can mean a lot of other things as well. So as you might know from there not being any of this in actual roadways, this was harder than we thought. So let me recap a bit as to this sort of phase of autonomy-driven design, where we are, why we thought this was a good idea, and what we can learn from it. So I'm sure many of you have seen this before. This is the Gartner hype curve. This describes the life cycle of a technology, which includes the hype stage, which is when expectations for this technology are inflated. So there have been multiple waves of hype for roadway autonomy. This is not the first. This is perhaps not the last. But this wave sort of started and kicked off with the DARPA Grand Challenge, an urban challenge, of which Stanford has had an immense history, around 2005. And something like a decade later, we start seeing articles of this flavor. This is a Business Insider piece titled, Wide Adoption of Self-Driving Cars Could Be Only 5 Years Away. Okay, so that didn't happen. A few years later, we had the very unfortunate Uber self-driving car crash, which struck and killed a pedestrian, Elaine Hertzberg. Causation or correlation, I don't know, but this coincides with a lot of the dip then in the hype for autonomous driving. Here we are today, still somewhere in this area. So roadway autonomy has sort of been through a lot, and I want to sort of recap why we thought this was a good idea, and again, what we can learn from it. The rationale for roadway autonomy really does have its merits. So let's review this. The first motivation is safety. So there are something like 43,000 fatalities on US roadways. This is from 2021. And there's this very famous study from NHTSA that concludes that human error is involved in about 94% of these fatalities. So it is very hard to conceive of an approach that would really get us to like 0 deaths without removing the human from the equation. Okay, so that's argument number one. The second one is cost. So I don't know about you, but I could use a 25th hour in my day. A bunch of studies conclude that Americans spend about an hour on the road. Okay, so one thing we could do is, well, we could all hire taxi drivers. That's very expensive. So travel time is by far the largest component of cost in the transport of people and goods throughout the country. Okay, so autonomy could potentially do something about that cost factor. Third being the environment, and there are many more along the lines of externalities. So the transportation sector is the largest contributing sector of greenhouse gas emissions in the US at this point, at around 29%. And a vast majority of these emissions, about 80%, are on roadways. So autonomy could enable all sorts of efficient use of vehicles. It could accelerate electrification. It could enable sharing of vehicles, potentially integration with transit. It could smooth traffic flow. It could help everyone use the right size of vehicles, platooning, so all sorts of these benefits. So this was the reasoning. Let's build autonomy, and then we get sustainable roadways. The question is in the premise. It's not really clear if this first piece is sort of technologically ready. So I'm going to argue that sustainable roadways, at this point, having given this sort of a few decades of time to develop, may require a different approach. So for lack of a better term, I'm going to call this use-driven design. So the way this works is, let's consider what we want to do in terms of improving roadways, and then let's design for that. So the logic is a bit flipped. Let's start with sustainable roadways on the left-hand side and ask, what do we need in order to enable this sustainable roadways? And if indeed it requires autonomy, then we're sort of stuck where we started out. But if not, then we might be able to make some progress. Okay, so it's a question of autonomy is sufficient, but is it necessary? So I'm going to look at a relaxed notion of autonomy, and specifically I'm going to look at the coordination of vehicles. This is something that autonomy enables, but potentially you don't need all of autonomy to do this. Okay, so you might need planning, you might need some degree of altruism, a few other components, but you don't need the full thing. That is what we think of as autonomy. Okay, and the question is, does the coordination of vehicles by itself enable us to achieve more sustainable roadways? If so, then the full thing of autonomy was, sufficient but not necessary. And if not, So this is what this talk is going to focus on, this coordination of vehicles. So the rest of the talk is going to be as follows. I'm going to sort of talk one at a time regarding how intelligent coordination of vehicles could achieve cheaper mobility, cleaner mobility, safer mobility, and so on. So along the way, there's going to be a bit of a detour because these intelligent coordination problems, these sort of multi-agent control problems, are annoyingly hard to solve. And so we also had to take a detour in order to sort of improve on these methods a bit. Okay, so I'm going to jump into the first part, which is on cheaper ways to achieve intelligent coordination for sustainable roadways. So this is joint work done with my students, Jung-Hoon, Siri, and Mayuri, and my collaborator, Roy Dong at UIUC. So this sort of has a couple pieces, but I'm going to focus on the average case performance analysis, and I'm just going to touch a little bit on the worst case stability analysis. Okay, so a very cheap way to coordinate vehicles is to simply give drivers an app. This is like much less of a requirement than full autonomy. If you look at this in the spectrum of the SAE levels of autonomy from 0 to 5, with 0 being fully manually driven cars to level 5, fully autonomous cars, we could think of this as something like level 0.5. Okay, so the car doesn't even have to have any level of intelligence. We just need a smartphone in the car. And this we might think of as probably the lowest cost near-term form of autonomy that we could possibly have. And the question is then, what can this do? So what we know from my work as well as others is that with level 5, sort of full autonomy, we can achieve system-level improvements, even with a fraction of cars that are equipped with this level 5 autonomy. We can analyze these traffic scenarios and see that by optimizing a fraction of cars, we can see system-level improvements in terms of speed and throughput. Okay. So this is sufficient. Level 5 is sufficient. Is it necessary? And the way we can analyze this is we can sort of slice this along the spectrum and ask, okay, is level 4 sufficient? Is level 1 sufficient? And so on. And so we're just going to go all the way to the other end because it's sort of appealing that it is also very low cost. Okay, so this brings us to the problem of what we call coarse-grained control. So the question is, to what extent can guided human drivers achieve the same kind of traffic optimizing behavior of autonomous vehicles? You can think of guidance as like a dynamic speed limit sign that's potentially even personalized to individual vehicles and drivers, or similarly on the acceleration side. Okay, this is not like a command. This is a sort of speed limit. The driver can still maintain safety and whatnot. So we consider this very simple model of coarse-grained control, just piecewise constant guidance. So some speed held for some time, another speed held for some time, and we're going to keep that time sort of constant. So this is also known as zero-order holds with a hold length of some delta seconds. And the goal is to design these coarse-grained control laws, pi sub delta. And the question is, how coarse can these instructions be such that we still achieve traffic optimizing behavior? So we can see that there's a hold length, and we can consider different problems with hold lengths like very, very high frequency hold lengths like 0.1 seconds all the way to sort of instructions that update every 40 seconds. And so on one end of the spectrum, you have sort of our model of an autonomous vehicle, instructions that are sort of changing so quickly a human cannot respond, up to a point where it's within the realm of work that instructions that humans could potentially follow. And so we're sort of just borrowing from some human factors research that 8 seconds is in the ballpark of what humans can respond to, and we're engaging in, we're designing some user studies now to confirm it for our setting. So the specific setting, or to be a bit more concrete about the setting, let's consider a traffic scenario, different networks where a fraction row of vehicles are guided and 1 minus row are not guided. And just recall, all the vehicles are human-driven now. The guided vehicles follow some actions from this learned controller, pi sub delta, where the action updates every delta time, whereas the unguided vehicles follow instructions according to a conventional driving model. So keep in mind now that the guidance type, the hold length, and the traffic scenario each is its own multi-agent control problem. So we solve this family of control problems by just independently learning these control laws using deep reinforcement learning. And in some cases, we can analyze the stability as well of the coarse-grained system. So I'm going to jump right to the results and then go back and talk a little bit about the methods. So let's look at this model highway. So this is a circular track. This is sort of like the cart pole of traffic. So it's like a simple environment where you would want your stuff to work before looking at something more complex. So a few observations are sort of nice here. So the coarse-grained guidance, the zero-order hold, actually coincides well with what's called sample data systems. And so there's a body of theory that's used to analyze these systems. And so in particular, these Lyapunov-Krasovsky functionals actually allows us to derive sufficient conditions for system stability for simple systems like this. Okay, so we can gain some intuition on whether or not the system should completely fall apart from a stability standpoint. Now on the empirical side, this is an easy problem in a particular sense. There is a fixed velocity that is optimal. So in principle, you could hold whatever length you want to. Okay, so here we have the hold length on the x-axis and the performance on the y-axis. So again, on this end, we have the AV. On this end, we have more human-like driving. So we expect the performance to decrease over as the hold length increases. But in this case, we should expect a straight line. Okay. So we have the optimal performance here, which is better than some baseline here. And what we see here is that, yes, there is a constant velocity that can maintain the speed throughout. However, when we issue some kind of acceleration-based guidance, what we see is actually it's still possible to do like almost just as well, even up to 40 seconds. However, when we apply sort of vanilla reinforcement learning, we see this hint of brittleness. We see that it's actually very, very jagged, this training curve. And keep in mind that the only difference between, say, this problem and this problem is just the hold length. The scenario is the same, the guidance type is the same. So it's a very, very small change to the environment. And training with reinforcement learning with our hyperparameter tuning and whatnot, it was actually rather disappointing for us. And so this actually motivated us to develop a method which we're calling the temporal transfer method. And this is the idea that, this sort of leverages the idea that these problems are more or less the same. Okay, the only difference is this hold length. So the idea is that for some target hold length, we should be able to find a policy, we should be able to solve a different problem and then sort of, if it's successful, transfer the result to this problem. So we're gonna leverage sort of two ideas here. One is that these problems are all more or less the same, but the coarser the problem, the easier it is to solve because the shorter the effective horizon. Okay, there are fewer decisions you have to get right for the same amount of time. So easier to solve, you can think of that as reducing the variance in training. However, because the instructions are coarser, this may introduce some bias. In particular, that the optimal performance could be lower. Okay, so what we're exploiting here is that there's some sweet spot. There's some sweet spot where the performance is still just as good or good enough that we can identify that sweet spot. It's easier to train, and then we can transfer to the target target hold length. So we can solve this using a stochastic form of binary search to identify this ideal source hold length. So using these ideas, we can then look at more sophisticated settings. So for instance, this highway ramp setting, now we sort of see the kinds of behavior that we expect, that on one end, we have high performance from the autonomous vehicle. I should say, red is without our method, blue is with our method. So we see sort of higher performance above some baseline, and that performance degrades as the hold length increases, which we expect. But still, for quite a bit of the what we understand now to be the human compatible region, there's still significant improvement over the baseline. So what we conclude here is that the coarse-grained guidance does preserve benefits from autonomous vehicles in terms of speed, fuel, throughput across a variety of traffic scenarios. The implication is that these guided human drivers could enable near-term, low-cost autonomy benefits, and that while vanilla reinforcement learning is brittle to even these very small changes, this temporal transfer method can improve the reliability of training these coarse-grained control laws. Yes?
So if people do not follow the guidance, like have you studied like kind of like
Yeah.
robustness to how much
Yeah.
people?
We're doing that work now. Yeah. So we don't have it yet, but yeah, we're doing that work now. It is important to factor in the robustness aspect. Yeah.
Maybe a related question. What are your thoughts on sort of the trade-off between giving this guidance to drivers and the extent to which it can draw attention away from the main driving task if they're sort of thinking, oh, I should speed up, I should slow down? Are you worried about sort of the distraction?
Yeah, I think there's a lot more that needs to be explored there. That's definitely outside of my wheelhouse. What we can do is we can actually analyze the resulting trajectories and whether those trajectories are safer according to these surrogate safety measures. So that's something that we are starting to do in a slightly different context. Yeah. Yeah.
Yeah. Do you think the time horizon is dependent on the environment? For example, the
Yeah,
highway
absolutely.
and
Absolutely.
road will be different?
The time horizon should be dependent on the environment, and also we are also thinking about making it adaptive, like based on the conditions, the real-time conditions. Right now it's just constant. So this is sort of like a very simple model that we could analyze. We have one axis where we can just sort of do a first pass at this problem. Yeah, I think there's a ton more that can be done here. Good. Okay, so we're gonna this like brittleness of reinforcement learning was very disappointing to us, and so we took a detour to try to understand this problem. And so in particular, this is a couple it's a couple lines of work where we are asking, is it just us? Are we failing to use reinforcement learning, or is it specific to our problem, or is it reinforcement learning? Like we want to tease apart like what the challenge was, and then some ideas as to how to sort of go about resolving this sort of brittleness. Okay, so this is the brittleness that we observed. And what we basically did, I'm going to be very brief on this, but we basically also identified brittleness of deep RL in existing benchmarks. Okay, so staying close to home, there's this benchmark on traffic signal control, controlling signals, not cars. And this benchmark includes both classical techniques as well as learning-based techniques, reinforcement learning-based techniques. And what we have done is we modeled, like basically you can think of the previous work as like, okay, when you vary the environment a little bit, the method no longer works. So we vary the environment a little bit based on a actual distribution of traffic intersections with our partners, Utah Department of Transportation. So we modeled sort of 160 intersections from Salt Lake City. And then all we're doing is we're taking these methods and we're reevaluating them on this like set of natural variations of this task of traffic signal control. We're retraining on each individual intersection. So we're not doing generalization. We're testing the robustness of the algorithm. What we find is that on a ranking from best to worst, while what's reported in the original benchmark is that these learning-based methods outperform this like the most prominent prominent classical technique of just fixed time control. When we reevaluate on the natural variations, the fixed time control and the classical methods together outperform all of the learning methods. And there's no specific pattern in what kinds of intersections the methods are failing in, and I think that requires further work. So for us, this is like not great news for reinforcement learning, but also tells us that it might not just be us. We also then looked at this for the popular control benchmarks, like this half cheetah and this pendulum and this cart pole, and we find that sort of by varying the length of the pole and the gravity coefficients and whatnot, you don't see as drastic of a flip in terms of like, oh, we should not use learning anymore. But we find flips in terms of like which methods are considered best, which reinforcement learning methods are considered best. Okay, so it's not just us. This sort of makes us want to throw reinforcement learning out the window, but we do like some aspects of it. So for instance, the learning-based methods are motivated by how rigid model-based methods can be to the assumptions of the underlying problem. And so what we would I just want methods that work. So it's very natural to ask, how about methods that sort of try to incorporate the best of both worlds, some sort of more hybrid methods that can both leverage the known problem structure in a sort of model-based sense, but also provide flexibility for the difficult to model aspects like model-free. And I think there's a ton of work in this space, but what we need this for our vehicle coordination problems. So with this, we need some kind of data set of problems with natural variations, and we are painstakingly creating some by modeling it with Salt Lake City and by looking at these problems, but there isn't sort of like an image net that you can just sort of download for studying this problem systematically. And that's a huge issue here. So what we're doing is we're faking a data set by looking to discrete optimization, which has documented over decades very natural variations of problems, including certain kinds of vehicle coordination problems. So this is sort of this area is a new one for me, but very, very compelling and very interesting. So consider this problem, the vehicle routing problem. This is like Amazon's package delivery problem that they solve every day, and Uber's problem and whatnot. So there are a lot of vehicle routing problems that are practical today. This problem has been studied for at least 60 years. And this is a nice tree of sort of almost like the evolution of this problem. As the world evolves, we realize, sometimes the vehicles have capacities. Sometimes there are time windows on when I need to deliver the packages. Sometimes the vehicles are electric. And so these variations of these problems have emerged over the last 60 years. So we have this sort of data set of natural variations that we didn't have to painstakingly come up with. But these are still open and active research problems. So what we can do is then we can sort of use this as a basis for trying to design methods that are more robust to natural variations. So what we're going to do is we're going to leverage an already effective strategy for many of these problems, especially at large scale, which is called large neighborhood search. So the key idea here is that large problems can often be decomposed into small problems. Okay? And what large neighborhood search does is it basically iteratively seeks a better solution by re-optimizing subproblems. So here's a big problem. We identify a subproblem. We solve it. We presume that we can solve a small problem, but we can't solve a big problem, or at least we can improve a small problem. And then we take the solution to that small problem, put it back into the big problem. Okay, and then we iterate. And what is typically done is that the subproblem is selected randomly, okay, or using a heuristic that's then customized for the particular application. So what we're going to do is we're going to learn the promising subproblem or subproblems to select. Okay, and I'm going to skip over all the details. There's a transformer, there's a regression problem, and whatnot, and skip right to the results. So for the most widely studied form of vehicle routing problem, which is the capacitated vehicle routing problem, fairly large problem, 2,000 nodes or cities, we can see that a learning approach can basically cut in half the solve time. So it could be twice as fast as random subproblem selection. Large neighborhood search itself is already very powerful. It already gives like a 10 times speed up over not using large neighborhood search. Okay, and then what we can do is we can use that same algorithm and we can train it again on variations of the vehicle routing problem, as long as you have big problems that can be decomposed into small problems. And we look specifically at CVRP with time windows as well as with pickup and delivery, and we again see speed up. So what's happening here is some kind of implicit learning of a selection strategy that's sort of customized to these different variations that at least outperforms the random selection. So what we learn is that deep reinforcement learning fails to be robust to these natural variations, including very small variations like the hold length of a problem, as well as the layout of the signalized intersection, these standard control benchmarks. And that this algorithm, which we call learn to delegate, which is this learning guided large neighborhood search, is more robust to natural variations of the vehicle routing problem as compared to random selection. So we're extending this idea now to a variety of settings, which includes different applications. We're looking at the multi-agent pathfinding problem in warehouse automation in collaboration with Amazon Robotics. We're looking at different subproblem types. So rather than which specific subproblem to improve, which type of subproblem to improve, as well as different algorithm backbones like branch and cut for solving mixed and interlinear programs in collaboration with MathWorks. Okay, so now I'm going to go back to the main theme of sustainable roadways and look at how we can use intelligent coordination for cleaner roadways. This is the biggest project I've ever undertaken, and it's still ongoing. And it's sort of split into sort of modeling pieces and control pieces, which will be evident. So let me remind you that we urgently need to decarbonize transportation, and it is the largest contributing sector. So what I'm going to try to exploit here is that traffic signals, you can think of them as a safety device. We need them for safety, but they induce stop and go all the time and basically everywhere. So it's about half of driving is near signalized intersections. And this back of the envelope calculation I found very helpful when I was designing this problem. But keep in mind, this is very back of the envelope. I take a recent survey for how much emissions can you reduce by controlling cars to mitigate emissions. And I did a very coarse meta-analysis. I took the plus minus 1 standard deviation of all the studies reported in this survey. And it gives me, 6 to 28% of emissions, of CO2 emissions is potentially avoidable. If you're optimistic, let's take the upper range. This says that about 15% of CO2 could just, not be used, not be emitted. It's not doing productive work. So what does this look like? Just sort of demonstrating the idea. So with fixed time traffic control, you have quite a bit of queuing at the intersection. Cars come to a complete stop. When they come to a complete stop, they have to fully reaccelerate. Alternatively, if you do some kind of what's called eco-driving, you can guide the cars in a way that when they get to the intersection is green. They didn't come to a complete stop. They may be slowed, but they don't have to reaccelerate from stopped. Okay, and that's where the emissions gain comes from. So this is, the research question here is, would coordinating vehicles to reduce the CO2 at intersections actually move the needle on climate change mitigation goals? Maybe it's a good idea, but maybe it's very niche in terms of where it is useful. So this was a curiosity to me because when I started looking at this, this is actually called eco-driving at signalized intersections. It's a bit of a mouthful, but there are some 50 papers on this topic already. Starting from a decade ago, but we don't see any of it in practice. And the question is sort of, why not? Is it not worth doing? Like, is it just not very effective? Is this like a topic of academic interest, or is it a missed opportunity? So the goal of this project is to investigate not how to eco-drive. A lot of the papers, a lot of the literature focuses on sort of the more detailed aspects of like, for this intersection, for this kind of equipment, for this kind of assumption, how do we implement eco-driving? But the question is, should we eco-drive? Is it worth doing? we are interested in, thus, what is the expected improvement of eco-driving over possible driving scenarios, the expectation. So what's sort of fun is that as I was doing literature review, this first reference here is titled Eco-Driving, an Overlooked Climate Change Initiative, published in 2010. This is actually referencing highways. And coincidentally, actually in cars, there often are these eco-driving modes for highways, for highway driving. And it would be amazing if there's an analog then for the other half of driving. Okay, so the central challenge of this work is basically how diverse the scenarios are. So we can look at first just the diversity of intersections. Every intersection has a different numbers of approaches, different numbers of lanes, different turning restrictions. And so just the intersections layouts themselves, these are all factors that affect eco-driving effectiveness. So we have to consider this sort of family of scenarios. And this is just the ones that I can picture very easily. There are additional ones, such as the slope of the roadway, which obviously would affect eco-driving, the weather conditions, the travel demand, vehicle types and age, and all this. So this is the central challenge. Looking at the literature, the first challenge is basically that eco-driving controller design has really focused on specific settings. So there's no known approach that can simultaneously handle this whole sort of large family of considerations. There's also no known approach that will scale to what we end up with is millions of different scenarios. So we take a multitask deep reinforcement learning approach, which I'll get into more detail later. The second challenge, which is really unfortunate, is that large-scale modeling of traffic has really focused on highways, at least in ways that are available to academic researchers. And so we need to actually do the modeling of the urban traffic, the driving that's actually near signalized intersections, as well as other eco-driving factors. So we do this modeling. It's a huge effort, and in order to do this at scale, because keep in mind we're still doing a rough analysis. This is not for implementation tomorrow. In order to do this at scale, we leverage OpenStreetMaps, which is great, but if any of you have used it, you also know how terrible it is. So it's an amazing resource, but almost all of the attributes are missing. Okay, so all this, most of the speed limits are not, there. Most of the lane lengths and turn configurations and all of this stuff is just not there. And so we devised a data imputation framework to impute many of the missing quantities. It's not perfect, but it is much better than just not having the quantities. This is only the static aspect of what needs to be modeled. There are also non-static aspects, such as, for instance, the percentage of vehicles that are being guided, the weather conditions, the season, the actual travel demand, and whatnot. Putting this together, this gives us about 1.5 million scenarios. And we were, just to give you a sense, this 27,000 intersections is about 10% of the signalized intersections in the country. So, and we chose the locations based on high emitting areas as well as data availability. So this is also not everything. There's a very extensive modeling effort that I'm not going to belabor. Here I have highlighted just the aspects that we discussed on the previous slide in terms of the static aspects. What was very fortunate for us and what actually allowed us to actually do this project as a small academic team is that many of the non-static aspects are actually already captured by an industry standard model maintained by the Environmental Protection Agency. So the EPA MOVES model captures, for instance, what is the emissions of a vehicle of a different age in driving on a road of a particular slope, of a particular type, at a particular humidity and temperature. So all of this detail is really well detailed in this model. This is an excellent tool. Its main challenge for us is, again, the scale, because we're working with 1 million scenarios. So we computed that it would take us about 9 compute years to analyze these scenarios by sort of directly using the tool. But what underlies the tool are emissions models, which are actually continuous functions. And so we engaged in this project to basically reverse engineer this EPA MOVES model and basically we learned surrogate models by fitting neural networks to to this tool and extracted the data to do this. Okay, so this allowed us to scale this up. Okay, so now onto the control part. We're just going to optimize the acceleration of the vehicles. Okay, the vehicles around us can lane change, but just to keep the problem a little bit more tractable, like the guided vehicles are only going to be optimizing the acceleration for the eco-driving purpose. Okay, so now we do our multitask reinforcement learning. What does this mean? So every traffic scenario, every one of the million scenarios is a task. And when we train, we sample for each rollout, we sample a new task, a new traffic scenario, and we add it to we use that data to train our policy. In order to make this not totally silly, we provide not only the vehicle's observations, but we also provide some information about that task to the input of the neural network. We use very standard training practices otherwise. So standard algorithms, standard training protocols for this like shared parameter multi-agent setting. Something that's non-standard is that the reward function design is really important given the brittleness of reinforcement learning. So we have sort of several works that are just focused on designing this reward function. This itself doesn't work well because very reasonably having one policy work over a million scenarios is sort of a tall order. So we extend this just a little bit to something that we are calling multitask reinforcement learning, which is multitask reinforcement learning on a partition of the space. This partition is sort of designed based on domain knowledge. We end up with something like 7 policies, so 7 partitions, which is still much less than the original set of scenarios. We're just partitioning based on the number of lanes and the number of phases in the traffic signal. Okay, so now on to the results. So the analysis here is for Salt Lake City. We're still crunching the numbers on the other ones. But what we see if sort of everyone is adopting this, we see something like close to 11% reduction in fuel. If we're comfortable just scaling this to the country, so we assume that Salt Lake City's intersections are representative of the country, we get something like 1.5% reduction in sort of US level CO2. Okay, so what does this mean to you? I, for a while, didn't know. I tried very hard to find a reference point. And sort of a gold standard that I found is from the venture fund that Bill Gates leads for climate change. And they are basically looking to support initiatives that has the potential to achieve 1% global greenhouse gas emissions reduction. So this is in that ballpark, which is, to me, very exciting. I can also say that at around 20% adoption, we see about 0.4% reduction in CO2. And this 20% gives us about 28% of the benefit. Okay, so there's some nonlinearity, and the intuition there is that if some vehicles are eco-driving, the vehicles behind them, even if they're not doing it themselves, might benefit as well. Okay. So we find that eco-driving at signalized intersections could potentially substantially contribute to transportation decarbonization. As part of this work, we did extensive modeling of urban traffic to fill a gap in traffic modeling beyond highways. And we developed these neural surrogates for this industry standard emissions model. And this actually we found later to be of potential high interest to air quality researchers because this tool is sort of the bread and butter for these researchers. But there's also a very high learning curve for this MOVES model, like maybe 1 or 2 months to learn how to use this. And so potentially easing the access to this. And then finally, this multitask reinforcement learning actually allowed us to scale up the analysis to 1 million plus scenarios. Okay, so then I'll talk about this last part. So this last part is my first foray into safety, which I'm now finding to be such an interesting area, especially when it comes to, especially really looking at this for roadways. So this is work that was just published actually like 1 or 2 weeks ago, done with my 2 students. And okay, so let me talk about why the safer challenge is so hard. The safer challenge is really hard because the bar is actually really, really high. Humans are just incredibly safe. So this is the statistic for the US. There's about 1 fatality every 80 million miles. This is like huge. This is 8 nines of reliability in terms of failure-free miles. This is 8 nines after the decimal point in terms of this probability. Okay, for reference, AWS is at about 2 nines. My Roomba is at about 1 9. And what about for autonomous driving? So here's the reference point that we have. Waymo over the last 10 years has driven 20 million miles. They've driven that much, okay? It's really hard to put a number, therefore, on autonomous driving. You can use proxies for this, and the proxies that I've seen put autonomous driving at somewhere between 2 to 4 orders of magnitude below human driving at this point. Okay. So without some breakthroughs, I think we need to be creative about what we expect from autonomy. Okay, so I'm going to try to be creative, and this is just the very first work that we have in this sort of direction of safety, which takes inspiration from air traffic control. Air travel is an even safer system. Its record puts us at 10 nines, even better than the 8 nines of human driving. Okay, so maybe there's some ideas that we can borrow from this sector. And the idea is we're going to bring ideas from air traffic control, which is aircraft. There's this thing called autopilot, but there are no autonomous commercial aircraft. There are 3 pilots in the cockpit. There's air traffic control on the ground. We're going to bring in some of these ideas. So let's bring these ideas from air traffic control down to dense roadway traffic. Okay, roadways are much more dense than the open skies. And the idea here, the central idea is let's complement the autonomous capabilities of vehicles with remote supervision from expert operators. So let's not give autonomy full responsibility. Let's also not give infrastructure the full responsibility. Let's see if we can get the best of both worlds. So I'm looking at a very specific question right now. So the question is, right now we do have a operator for a car. So it's like a one-to-one kind of deal. Imagine that you were to take this operator and put them, him, her, into a call center, basically, with a steering wheel. Okay, everything's perfect. Communication's perfect. Sensing's perfect. Okay, so let's make all the clean assumptions. The question is, in principle, how many operators would you need to supervise your fleet safely at the reliability of humans, at human now? If it's one-to-one still, that's not good. We just incurred additional cost of all the communication infrastructure and whatnot. So this is sort of the question. As the AV fleet size grows, how does the supervision scale? Okay, so this is the scalability of supervision problem. So we model this using a queuing model. So we can think of arrivals to this queue as risky events, okay, risky events that need to be supervised. And we have some number of operators, M, that can supervise these. And we're interested in the probability that there are so many risky events that arrive that there aren't enough operators. Okay, so what you can model this as is a queue without a buffer. So the buffer is exactly the size of the number of operators. So if any new risky event arrives, it does not receive service. So effectively, we're interested in the probability of service loss. That's the probability that the system already has M risky events. Okay, and reliability you can think of as 1 minus this piece of M. Okay, and then now we can set that to our 8 nines or something. Okay, so specifically we're going to look at the closest to practical setting for autonomous driving, which is highways. And we're specifically going to look at a dangerous maneuver on highways, which is merging. Okay, we're looking at merging on. You can also think of it as merging off. Okay, so the first thing to observe is that we're going to assume that once on the highway, the car can drive safely by itself. So we're just looking at merge conflicts as our risky events. So the first thing to observe is that you don't always need to supervise the vehicle. Okay, if there's no merge conflict, Okay, so if there's no merge conflict, then there's no need to supervise. And we're going to determine whether there might be a merge conflict using conservative worst case forward reachability, okay, giving the operator enough time to sort of understand the scenario. Okay, so in the interest of time, I'm going to be very brief on the details. The question is, what happens when adoption grows, when AV adoption grows? So intuitively, more adoption means there are more cars that need to be supervised. So reliability goes down. When there are more AVs, you also have more AVs that can sense the environment and communicate, everyone's trajectories and whatnot. So the reliability goes back up at some point. These are these dipped curves. The even more interesting thing is, as you have more AVs, these AVs can start to coordinate. If you have two AVs approaching the merge point, and they're both AVs, one can just slow down and just let the other one go, right? They don't have to collide if that was the planned trajectory. And as you have more AVs, the probability that it's two AVs that are merging at the same time becomes higher. Okay, so these reliability curves for the same number of operators gets shifted up with this kind of coordination. And what we find through some numerical examples, we didn't cherry pick this, but we also didn't explore this extensively, is that it could make something like a 6 orders of magnitude difference in terms of reliability for a fixed number of operators. Okay, so this is a particular setting that is where 50 supervisors achieves the 8 nines of reliability, whereas without cooperation is at like 99%. And this setting corresponds to a scaling of about 42 vehicles per operator. And keep in mind that the original, the status quo is this 1-to-1. Okay, so that's all I wanted to say about this first foray into safety. I'm finding this to be such an interesting area. There's so much more to be done. This is, to our knowledge, the first queuing theoretic model for supervision and coordination of autonomous vehicles. And I think it's a really interesting concept to start thinking about these relaxed notions of autonomy, enabling sort of a richer design space for safer roadways. So I hope that this conveyed to you that autonomy is sufficient, but it may not be necessary for us to make substantial progress on sustainable roadways, and that this idea of use-driven design, of considering what we want to design for in the first place and then designing for it, can bring us quite far. Thank you.
Hey, Cathy, great talk. I have a quick question about the remote supervision and coordination part that you were talking about. So the remote supervision, why do I don't fully get why you actually need the remote supervision and why you can't get the cars to just do connected vehicles and communicate with each other. Also, if you have a remote supervision, then what is the visibility that they have, right? They'll probably maybe I didn't get some part of that. I'd imagine that it would be actually kind of hard to do the remote supervision.
So I didn't get the first part of your question. Why not the?
Yeah, why not just I thought if you just do the connected vehicles angle and cooperate, you wouldn't necessarily need remote supervision for the type of highway merging that you were talking about.
Basically because the vehicle we're doing this in mixed traffic, so the vehicles may not be connected.
Okay, got it.
And so as the AV penetration grows, the probability of the interaction with a vehicle that is connected grows, and that actually eases supervision quite a bit. Mm-hmm. So when there is coordination, then we don't have this problem. Mm-hmm. But when we interact with a human driver, then we have this remote operator. We're not assuming anything about those vehicles. Mm-hmm. Then there's no sensors on them and whatnot. But for a practical implementation perspective, in terms of field of view and occlusions and whatnot, I think we have to be more creative about where do we put sensors potentially on the infrastructure, on the on-ramp and whatnot, so that there is full visibility to the operator. Cool. Yeah, great question.
How do you evaluate? But sorry, I'll ask a follow-up. So you talked about some of the evaluations and the simulation environments, but have you guys started looking at real evaluation for the methods?
No. This is the very first.
But are you envisioning doing real? How do you go about it?
It's a very good question. I'm interested, but I think we are still pretty early. Yeah.
That's interesting.
Yeah, happy to talk about it if you're.
Yeah, let's chat about it.
So, since the mic is here, something, kind of related to this real evaluation. I'm kind of curious. How do you envision this? Sort of translating into something that autonomous driving companies that are starting to do sort of early prototype deployments could learn about. My understanding from the early Waymo prototypes is that once they started having these cars in, the Phoenix area, that were driverless. Actually, they didn't have a car, and the person could get picked up and dropped off. Basically, at first they had a chaperone car following, just a few meters behind in case anything happened, so that they could quickly jump in and whatever, resolve issues. Obviously, that's not very sustainable, and you still probably want to have some kind of supervision. Is this something that you're thinking could allow this to actually scale, actually have people on the road doing this kind of following? How do you think about that in practice?
Very good question. So one thing that's helpful in this concept is that this is basically a fixed location. This is like the on-ramp. Okay, so it could be scalable in terms of supervising, in terms of like additional supervision, like right at the on-ramp, or right at several on-ramps, let's say. So I think that's part of it. I haven't thought about this at all, so this is just like on the fly thinking. In terms of coordination so let me back up a bit and give a bit of context for like where this idea is sort of coming from. This wave of autonomy has been this like autonomy-driven. So autonomy, then do things. And this autonomy is sort of assumed to like require no support from infrastructure. And that's sort of what a lot of the companies like really would like. The previous wave of roadway autonomy was basically infrastructure-based. This is the California Path project. And there, the issue is that it required basically a dedicated lane of the highway to fulfill this automated highway scenario using technology that was already more or less mature 30 years ago. But we could not justify the economic cost of either building a whole extra lane or reducing highway capacity by a third or whatever to facilitate this new technology that would have almost zero cars on it at most times. And so where I'm coming at here is, it's clear it has to be done in mixed traffic. It can't be a dedicated infrastructure. Can we get away with a different kind of infrastructure, communication infrastructure? And can we complement where autonomy is now with infrastructure support in a cost-effective manner to envision a concept for automated highways? That's sort of where this is coming at. And I think that there are a lot of interesting questions at the sort of testing and realization of this. I think that where I am right now, I think there's still so much to conceptualize, even at this higher level of like designing the system, sizing the system, figuring out whether this concept could see the light of day. And sort of that's where I am now, and that's potentially why I don't have responses to all of the lower level questions. But I think a little bit about the, like whether 5G, 6G is like sufficient to support this kind of thing and stuff like that.
Yeah, I have a question on also like evaluation of like the first work you talked about, like you mentioned about user studies. Are you doing this with like just the guiding stuff? Is that with real drivers?
Yeah.
And I guess that the question is, do you foresee any fairness issues with this kind of instructions? Like if you personalize this kind of guidance, the driver might think, I'm like sacrificing something like my like time for others. Like
I think this is a little bit different. Yeah. So yes, we're doing this with actual drivers, and two, we in collaboration with some folks, and we are also doing the equity aspect. I think is a little bit different from routing games. So with routing games, it's like, okay, people participate, and the people who are willing take the longer routes, and they're really sacrificing their travel time for the benefit of others. This one, we're not changing their routes. They're basically getting there at the same time as everyone else. We might even be able to leverage something like carbon credits to compensate for those who participate if that were to work out. So I think there is a realm in which the equity aspect could even be progressive, as long as they have a smartphone. Yeah, they have a car and smartphone. Yeah.
I'm sorry to do this. We're going to need to relinquish the room. If there are more questions, we can take them on the patio.
Thank you so much.